Our brain is a computational device, and our mind is nothing other than the physical operation of our brain. So our brain is somewhat like a computer, except it's obvious that our brain operates on very different principles than a computer. If our brain did operate like a computer, you'd think that we'd recognize artifacts in our experience that we see on digital computers. For example, the pixelization you see when you zoom in an image too close, or the jaggies when you draw a line in your graphics, or aliasing effects in sampling. Do we see such effects in our experience of the world? Should we expect to see some? Generally, people think the world around them looks pretty much the way it actually is. Where are these artifacts, if there are any? Well, perhaps we're just not recognizing them, even though they're there right in front of us. For example, the phenomenon of music, I believe, is an artifact of how we process temporal information. Dance seems to exhibit the primitives of motor control in cyclic phases that we find to be beautiful. Visual ornament, Gothic cathedrals, ornamental patterns appeal to our senses, and that too, I think, is an artifact of how our mind works. The fact that we could recognize the symmetry in a kaleidoscope is a clue as to how our vision works. And in drug hallucinations, people often see periodic and symmetrical patterns. But the queen of all artifacts of our mind that are a clue to how our brain works is mathematics. Now, the mathematics I'm talking about is not the gobbledygook equations that we learn in school. What I consider to be the real math is the pristine images represented by those equations. Mathematics has got a peculiar dual aspect, both as a system of symbols and spatial concepts. Our mathematical education tends to focus on the symbolic manipulation of symbols, and I think this is an error. The intuitive spatial aspect of math is largely ignored as if it were irrelevant to mathematics. But according to my view, the spatial aspect, the intuitive aspect of math is the real math. Mathematics is fundamentally a system of mental imagery that defines spatial patterns, analogous to the function of a ray tracing algorithm that is designed to generate synthetic images. This aspect of math connects mathematics back with perception. Consider the concept of number, quantities that we represent with numerical symbols on the page. But the values of the numbers are actually arrayed along the number line. Seen as spatial entities, numbers are like vectors from the origin. Spatial relations between distances relate directly to numerical relations. We talk of numbers that are greater than or lesser than other numbers, or numbers that fall in between certain bounds, or numbers that are double the size or half the size of other numbers. Mathematical relations between numbers have a spatial meaning to it, because the number line is more than just a metaphor. The number line is a direct representation of the nature of number and how it is represented in the mind. And that in turn is a hint as to the mechanism of math in the brain. Consider multiplication as an analog function. Here we have two numbers on the number line, A and B, and let's look at the value of C, where C equals A times B. If A is anywhere near 1, then C will be right on top of B, wherever B happens to be. If A is greater than 1, then C will be greater than B by the same amount, no matter what the value of B is. And if A is less than 1, then C will be less than B by the same proportion. There's a symmetry to this, because if we reverse the positions of A and B, now we'll see if B is equal to 1, then C remains equal to A, whereas if B scales larger or smaller than 1, then C does the same. There's also a 0 point. When any of the factors are 0, then C goes to 0 also. And then there's the negative zone, where you have a mirror symmetry reflection about the origin, except if both numbers go negative, you'll see A and C cross at the origin, because a minus times a minus makes a plus, so the situation is not perfectly symmetrical. The scaling function of multiplication works just like an old-fashioned pantograph used to make copies of maps in the olden days. This is the way that multiplication scales value in and out from the origin. P2 is double P, and this is P3 is 3 times P, and that's the analog view of multiplication. We now know that all numbers are complex. That means they can have an imaginary component, and we can see the meaning of this in complex multiplication, where the angle of A, shown here as the blue wedge down here, and the angle of B, the red wedge, the angle from the origin to B, are added to make the angle C. See how I can make C go round like this with either A or B, because it's a rotational multiplication. It's a multiplication that goes round and round instead of in and out. Actually, this is very much what the pantograph does as well. The pantograph really works very much like complex multiplication. You can get a better idea of what complex multiplication is doing if you turn on a set of random points and multiply them all at the same time. These are all complex number points, and multiplying all by A. If A is 1, they all stay where they are. If A is greater than 1, they all move out away from the origin. If A is less than 1, they shrink in towards the origin. And if A goes negative, then they all reverse upside down and backwards through the origin. This is a very peculiar computational operation. The pantograph reveals what complex multiplication is doing. In the olden days, the pantograph was used to make copies of objects by just tracing from one to the other. And here we see the pantograph making multiplicative copies of this circle. And here we'll do a square. And you see that the pantograph is kind of pretending to be a perfect copier, an affine copier, but it does so by pivoting from a center. One could imagine a perfect affine pantograph, which would work like this, making an exact copy of objects instead of a multiplicative copy. And here we see the difference between affine spaces and vector spaces, that the affine space, every point is the same, it has no origin, but the vector space does multiplication from an origin. This is the essence of what complex multiplication is about. It's about relating the allocentric Euclidean external world to the egocentric polar coordinate system of the self-centered world. Multiplication reveals even more extraordinary properties when performing multiple multiplications all at the same time, as in linear algebra and matrix multiplication. Starting here with a standard 3x3 matrix. This one's the identity matrix. And up here we have an array of sliders that control the magnitudes of these coefficients. So I can slide these sliders here, and you see the effects on the numbers here. Now the way to visualize this 3x3 matrix is as a three-dimensional structure, and the numbers on the main diagonal here are three vectors stretching out in XYZ directions, And in the case of the identity matrix, they are all value 1. And what this matrix does is it performs a spatial transformation on any three-dimensional point in this space, multiplying its 3 dimensions by these 3 coefficients. So for instance, this here is the unit point at location 1, 1, 1, and if we multiply its xyz coordinates by 1, 1, 1, the point remains where it started. So this is the null operation. It doesn't move points at all. If I change the x magnitude over here, you can see that that scales the point outward along the x-axis. And if I make it 0, then the point loses its x-coordinate. And if I go negative, it goes negative. But you can see the effect of this multiplication more clearly when you look at a whole array of clouds. Here's a point cloud. And you notice that as we scale the x magnitude in and out, the cloud stretches in and out from the center. And when we get the x magnitude to 0, it's a projection onto the YZ plane. There's an intimate connection between the concept of multiplication and projection. And of course, the same thing occurs the same way in Y, stretching in and outward from the origin, and in Z, stretching in and outward vertically. And of course, if any of these numbers go negative, the entire cloud passes through itself and makes a mirror image replica of itself across the other side. If you scale all 3 of the main diagonal terms at the same time, that scales the entire, all the points in and out from the origin. And of course, there's also a 0 and a negative where everything turns upside down and backwards. What about off-diagonal terms like this xy magnitude right here? This is a cross multiplication between the x and y dimensions. It shifts points in parallel to the y-axis based on their x coordinate. So the best way to visualize this is, let's make this point equal to 1, and we imagine this as a vector starting at the point x equals 1 and stretching in the y dimension, and the length of that vector is proportional to the magnitude of this coefficient. Now, in fact, a better way to visualize this is as a line, a skew line, and you can see how it multiplies points farther with larger x-coordinate more in the y direction, and ones with a lower x-coordinate less in the y dimension. For example, if we turn on this row of points, we'll see how the row of points is skewed by this skewing transformation. And there is a complementary skew, the yx skew over here, which shifts points in the x direction based on their magnitude in the y direction. So this too is best visualized as a skew line. These are skewing transformations. So what we have here is an extremely sophisticated three-dimensional image representation and manipulation system that is based on one rather simple principle of analog multiplication. In analog electronics, multiplication is simply analog amplification or amplitude modulation. Here we have a sawtooth generator, signal generator, that generates this sawtooth signal, which is split into x and y components. Here we see the 2 components. And then we have operational amplifiers, op-amps, to do the multiplication by a constant that's controlled by these 2 sliders over here. And these x and y sawtooths are then plotted against each other to define a vector pointing in a certain direction in space. Now, when we modulate the components, here I'm modulating the magnitude of the x component, and you can see it changes the angle of the vector. And if we slide into the negative range, see how the x sawtooth is upside down now, and the vector is over in the second quadrant. Now, if we move the y coefficient into the negative, then the vector rotates into the third quadrant. And finally, if we reverse the x back to positive again, then we get to the, sorry, this is the third quadrant. And then we bring the y back to positive, we get back into the first quadrant. So what we have here is a system that's very suggestive of the nature of analog multiplication and vectors, revealing a basic principle of representation in the mind. Now, there's one peculiarity of this system, which is that the matrix operations do skewing, whereas complex multiplication does rotation. Why do we have two separate systems? Some problems we solve with one and others with the other. Now, you can imitate the rotation with the matrix system if you use the proper sine and cosine values in the coefficients, but that requires that you have some kind of lookup table or some other independent computation of the sines and cosines, whereas in complex multiplication, they are just implicit, invisibly part of the multiplication. Now, there's one system that unites the skewing of matrix algebra with the complex numbers, and that is Clifford algebra, the most extraordinary advance in mathematics that virtually nobody has ever heard of. Clifford algebra, also known as geometric algebra, is a most extraordinary synergistic confluence of a diverse range of specialized mathematical fields, each of which has its own methods and formalisms, all of which find a single unified formalism under Clifford algebra. It is a unifying language for mathematics and a revealing language for physics. Unlike standard vector analysis, whose primitives are scalars and vectors for representing points and lines, Clifford algebra has additional spatial primitives for representing plane and volume segments in 2 and 3 dimensions, and it can be extended to any number of higher dimensions by the same basic scheme, and they do with remarkably useful properties. We begin with a historical summary of how these ideas came about. It all started when the solution to certain equations came out to be equal to the square root of -1, which seemed to be an impossible number. But if you assume that this number exists, and that in every other way it's just a regular number, with the only exception that it squares to negative, then 1 times I would have to be equal to I. I times I, by definition, is -1. -1 times I would be equal to -I, and -I times I makes -1, which brings us back to 1. So multiplication by I is equivalent to a 90-degree rotation on the complex plane. Later, it was proposed that numbers could rotate part of the way, and this creates compound numbers that have a real and an imaginary component. But the peculiarity of this system is that the real numbers and the imaginary numbers operate by different rules. Multiplication of reals scales their length in and out, whereas multiplication of the imaginary dimension rotates round and round. Meantime, in another branch of algebra, Josiah Willard Gibbs was working out vectors as we learned them as directed line segments in 2 or 3 dimensions. These are also compound numbers with x, y, z components. And he discovered that you can create a system of addition and subtraction. You can add these vectors as if they were regular numbers, and it made a certain spatial sense. The question was, can you multiply them? And Gibbs came up with the dot product and the cross product that we all learned in school. The dot product was inspired and has been adopted in Clifford algebra. The cross product, on the other hand, is fundamentally flawed, basically because it only works in 3 dimensions. If you do it in 2 dimensions, it jumps out of the page at right angles to the page, and it doesn't really work in 4 or higher dimensions either. Meantime, in yet another branch of mathematics, William Rowan Hamilton was very impressed with the elegant complex multiplication, the rotational multiplication of complex numbers, and he came up with a three-dimensional complex number system, I, J, and K, each dimension of which operates exactly like complex numbers. He had the circular rule that I times J equals K, J times K equals I, and K times I equals J. This is a circular multiplication that goes round and round all three of them, just as each one goes round and round by itself. I squared plus J squared plus K squared equals IJK, which comes out to -1. Now, Hamilton ran into a problem defining division for these entities because although A times B equals C, the inverse, C over B, does not produce a single unique value, but a whole range of possible values. After many years of frustration, in a flash of intuition, immortalized by a plaque on the Broom Bridge in Dublin, where the intuition first struck him, Hamilton realized that he needed one more scalar value to provide a scale for his complex vectors, so he defined a compound number in the form of a scalar, plus bi plus cj plus dk in imaginary dimensions, and the quaternion was born. All this occurred in an era when the theory of relativity was first emerging, and Hamilton incorporated a relativistic concept in his quaternions by expressing rotations not with reference to a global XYZ coordinate frame, but relative to the current orientation. For example, the orientation of an aircraft in flight, if it's described in Euler angles, as pitch, roll, and yaw angles relative to external coordinates, then there's a problem known as gimbal lock when the aircraft is headed either straight up or straight down, where it has no defined orientation. Hamilton introduced another innovative departure from conventional mathematics by proposing a multiplication which is not commutative, i.e. that A times B is not equal to B times A, but neither are they unrelated, because in fact A times B equals negative B times A, where negation corresponds to a reversal in the direction of rotation, just as negation of a real vector reverses its orientation. These intriguing concepts were incorporated into Clifford algebra. Now, a word on the mathematical concept of closure, an idea that will be significant throughout this presentation. In algebra, closure refers to operations on an algebra that remain within the algebra. For example, the natural numbers are closed under addition because the sum of any two natural numbers is also a natural number. But they are not closed under subtraction because if you subtract enough, you can fall right off the end of the number line. Integers, on the other hand, which include negative numbers, are closed under addition, subtraction, and multiplication. But they are not closed under division because certain quotients fall between the cracks of the integers. But that is not the only kind of closure in math. There's closure in our numeral system where when we run out of digits, we just put a 0 and carry to the next column. There's closure in an odometer where each wheel flips from 9 to 0 and the whole register flips from 99999 to 00000. There's also closure in digital registers that also flip from FFFF to 0000. It's a computational principle that prevents the calculation from running off the edge of the page or the register, allowing infinite calculation with a finite precision. And there's closure in a multiplication that goes round and round instead of in and out. It defines a continuous space like a section of the x-axis, but it is a closed dimension that is finite but boundless. This will turn out to be very significant. Meanwhile, over in yet another branch of mathematics, Hermann Gunther Grassmann was coming up with an alternative form of vector multiplication, which he called the wedge product, in which one vector is slid across the other, or the other across the first, in order to define a little plane segment, a segment of a plane, the plane that contains both of the vectors, and the area of the plane is the product of the length of the two vectors. These wedge product entities are also known as bivectors, and bivectors can be added and subtracted just the same way that regular vectors can. Furthermore, if you do a wedge product between a bivector and a third vector, that creates a trivector, a volume element, a finite volume element defined by the three composing vectors. And the same scheme can be extended to higher dimensions without limit. It was William Kingdon Clifford who took all the ideas of his predecessors and put them together into a single self-consistent system composed of a hierarchy of compound numbers known as cliffs, or multivectors, that range from 0 dimensions, equivalent to a scalar, to 1 dimension, which is a vector, to 2 dimensions, which is a bivector, to 3 dimensions, a trivector, and so on to any number of higher dimensions. In order to attain the kind of closure seen in quaternions, you have to decide from the outset how many dimensions you want to use for your problem. So for example, two-dimensional Clifford algebra, or CL2, wraps around at 2 dimensions so as not to protrude out of the plane into the third, whereas three-dimensional Clifford algebra, CL3, has closure in 3 dimensions so as not to protrude into the fourth. Just as a real number can be considered as a complex number with 0 imaginary component, a cliff can be considered to be composed of higher order cliffs up to the grade of the algebra you choose, even if many of them happen to have 0 coefficient. Clifford algebra of 0 dimensions, CL0, is just a regular scalar. Clifford algebra of 1 dimension, CL1, is composed of a scalar and a vector. CL2 is composed of a scalar, 2 vectors, and a bivector. And CL3, three-dimensional Clifford algebra, consists of a scalar, 3 one-dimensional vectors in the 3 prime directions, E1, E2, E3, and 3 pairwise wedge products of E1 wedge E2, E1 wedge E3, E2 wedge E3, and then finally there is a trivector composed of E1 wedge E2 wedge E3, and so on up to higher dimensions. Let's take a closer look at CL3, Clifford algebra, in 3 dimensions. There's a scalar, E, and then 3 orthogonal basis vectors, E1, E2, E3, then 3 bivectors obtained by pairwise wedge product of the basis vectors, E1 wedge E2, E3 wedge E1, E2 wedge E3, and finally there's a trivector that is defined by the wedge product of all 3 basis vectors, E1 wedge E2 wedge E3, and this trivector has a peculiar property. It's called the pseudoscalar, capital I, because it kind of represents the entire space. For all the different cliffs of the various grades, there are basically 2 ways that cliffs can interact. One is by addition-subtraction, and the other is by multiplication and division. Here we see scalar addition. A scalar plus a scalar makes another scalar. If you have a scalar plus a vector, then that makes a compound scalar and vector entity. If you add 2 vectors, they make a third vector by regular vector addition. A vector plus a bivector makes a vector bivector compound structure. And a bivector plus a bivector, they add just like vectors do. So this is addition and subtraction. Now let's take a look at multiplication and division. A scalar times a scalar makes a scalar. A scalar times a vector does something interesting because a scalar, a non-spatial entity, multiplies with the spatial vector and it modulates the magnitude of the spatial structure. A vector times a vector makes a wedge product, a bivector. A bivector times a scalar scales the area of the bivector. And a vector times a vector times a vector makes a trivector, a 3-dimensional volume element. Now here's a peculiar thing. A vector times a vector times a vector times a vector collapses back down to a scalar, and this is the closure in Clifford algebra that prevents a CL3 three-dimensional Clifford algebra problem from protruding into the fourth dimension. When you multiply two parallel vectors, the product collapses to a scalar. A times A equals 1. This represents the fact that A multiplied by itself makes a perfect match. It's a perfect match to itself. Multiplication of a vector with a bivector rotates the vector through an angle. So, for example, here's vector A, and here is vector B. And if we say A times B equals C, this arrow here represents bivector C, which represents a rotation from the angle of A to the angle of B. Now, if we apply this bivector rotation to B, then we take B times the bivector C, starts at B and rotates through the same angle as the angle C, and that creates D, which is B times C. Since Clifford algebra multiplication is anti-commutative, it's important to distinguish A times B from B times A, depending on which is the pre-multiplier and which is the post-multiplier. For example, A times B is a rotation from A to B. When applied to A as an A times B, it rotates A into B, or B equals A times B. But the term can be grouped differently by moving the parentheses. For example, A times B. Since A times A is 1, A times B equals B, which produces the same result, so everything works out in the end. Just as with Gibbs vectors, with their distinction between the dot product and the cross product, the geometric product of Clifford algebra is also has two components, a dot product and a wedge product. And the combination of the two, A times B, the geometric product, is defined as A dot B plus A wedge B. Now, the inner product is kind of a grade reducing operation that kind of projects vector B onto vector A. It's a grade reducing operation which ultimately reduces to a scalar that represents the match, the amount of similarity between the two vectors. The wedge product, on the other hand, is an outward grade expansive operation that spans the space between the two vectors. It's a measure of the difference between the two vectors in the sense of what you'd have to do to A in order to transform it into B. Now, these two processes, these two products are not only complementary by desire, but even by definition, by design. That A dot B, the dot product, is defined as the average between A times B, the geometric product, plus B times A, the reverse of the geometric product. If you add a vector to its reverse, then that cancels out the asymmetrical component and leaves only the symmetrical component. In A wedge B is defined as the geometric product A times B minus its reverse B times A. So when you subtract a product from its reverse, then that eliminates the scalar product and leaves only the asymmetrical component, the wedge product. The wedge product is a grade increasing expansive operation. Scalar, wedge, a vector makes a vector. A vector, wedge, a vector makes a bivector. A bivector, wedge, a vector makes a trivector. A dot product is a grade reducing or collapsing operation. A trivector dot a vector makes a bivector. A bivector dot a vector makes a vector, and a vector dot a vector makes a scalar. Here's a graphical animation of two vectors, A and B, as one of them rotates around the other. And we see displayed the wedge product as this circle over here, and the dot product represented here as a vector. There should actually be just a magnitude without a direction. But you notice how the wedge product changes in polarity and direction of rotation as the vectors cross over each other and go the other way. And likewise with the scalar reaches its maximum when the two vectors are parallel, or a negative maximum when the two vectors are antiparallel. This is the geometric product. Clifford algebra has been characterized as a reflection algebra because its most primal operation, vector multiplication, seems to mimic a simple reflection. If red vector C is equal to B times A times B, it is a reflection of A through B because the angle from C to B is the same as the angle from B to A. We are dealing here with unit vectors so as to avoid additional scaling resulting in pure rotation. This Clifford vector multiplication animation shows the reflection of A in B occurs like a reflection in a plane surface normal to vector B. This red vector A and this yellow vector B are multiplied as in B times A times B that takes the vector B and rotates it through the same angle as the angle between A and B. So you see that this B times A times B is always double the angle between A and B. It's as if there was a plane mirror attached to the base of vector B, and vector A was reflecting through that mirror, thus revealing that this Clifford algebra multiplication is fundamentally a rather simple process. There are a number of algebraic concepts that are revealed to have spatial equivalents in Clifford algebra. For example, negation of a number is equivalent to a reflection across the origin. Rotation by 180 degrees is also like a reflection across the origin. That rotation by 180 degrees is equal to negation. This means that rotation by 90 degrees is equivalent to rotation by the imaginary number, so that two rotations of 90 degrees reverse your direction. This completely removes the mystery of that peculiar concept of the square root of -1. It's also a peculiarity of Clifford algebra that it doesn't really deal in angles, but deals with them as ratios of sides. So an angle is expressed by its x and y components, suggestive of a Cartesian plotting scheme. The purpose of this seems to be to relate the allocentric city block Cartesian coordinate system with the egocentric dartboard polar coordinate system, expressing one in terms of the other. This is an algebraification of geometry, treating the rotational dimension like the translational dimensions with a reversal of direction with negation. This is very strange. Another peculiar concept in Clifford algebra, it actually exists in regular algebra also, is the concept of the dual as a kind of like a orthogonal complement, like a particle-antiparticle pair, the yin and yang. For example, the dual of a vector is a bivector, and the dual of a bivector is the vector. The dual of a scalar is the pseudoscalar I, and the dual of the pseudoscalar collapses back to a scalar. It's easy to calculate the dual of a Clifford algebra object by essentially multiplying it by I, the pseudoscalar, and that basically collapses all the dimensions that are occupied, leaving only the complementary dimensions that are not occupied. This, too, is a consequence of closure. Another curious algebraic spatial concept is the concept of a null space, the inner product or the outer product null space. For a vector v, the inner product null space is defined as the set of all of the vectors whose dot product with v would be equal to 0. So this is essentially the infinite plane that is at right angles to the vector, kind of an extension of the idea of the dual of the vector. Similarly, the outer product null space is the set of vectors whose wedge product with the vector equals 0. So for this vector here, it's the infinite set of vectors that are parallel to this vector. The dual of a vector is an area, but the inner product null space of a vector is a plane. Next, we come to the inverse function, a concept that you learned so long ago that you probably can't even remember learning it. But in all the time since then, nobody has ever pointed out to you that it's a conceptual impossibility. Supposedly, for every value x in the range from 1 all the way out to infinity, there's a unique and singular value 1 over x, the reciprocal of x, but that reciprocal falls in the finite bounded range between 0 and 1. This is a point-for-point, one-for-one mapping between an infinite space and a finite interval. It's as if you took the number line from 1 to infinity, made a mirror image reflection of it, took the reciprocal of that, then we effectively put a bracket beyond infinity and squashed the reflection back down to a finite range so that the entire reflection is squashed into the unit interval. This is a completely impossible operation because it pretends that it's possible to place a bracket beyond infinity and to squash infinity back to finity, a finite range. And on our familiar number line, the same operation is done in the negative direction too. This creates a double mirror image of the whole number line from negative to positive infinity, excluding the unit radius, all packed within the finite range of the unit radius from -1 to +1. This is an extraordinary paradoxical impossibility, but it is the impossibility that brings closure to multiplication, that offers a reciprocal to multiplication as if every positive and negative number had a reciprocal value that falls between positive and negative unity, and the fact that every number has its reciprocal is what makes it possible to multiply and divide both sides across the equal sign, to calculate forward to compute implications as well as backward to impute original causes. This incredible, impossible reciprocal function was already present in scalar algebra that we learned in grade school. What Clifford algebra adds to this concept is a circular symmetry, like a set of number lines rotated through all orientations, tracing a unit radius circle at the center, within which is a conformal reflection of the infinite surrounding space. For every xy point in two-dimensional space that falls on some radial ray from the origin, there is a reciprocal point that falls on the same ray in the same direction from the origin, but with radial distance from the origin that is the reciprocal of the distance to the point, just as occurs on the regular number line itself. If the original point is greater than unity, then its reciprocal is always less than unity, and vice versa, because, by symmetry, the reciprocal of a reciprocal gets back to itself. Clifford algebra generalizes the algebra on the familiar number line to an algebra that occurs symmetrically in all orientations equally, and thus merges algebra with its parent geometry to define an algebra of space. And this same concept extends naturally into 3 dimensions and higher, where the central unit radius sphere, or hypersphere, contains within it a reciprocal inverse conformal reflection of the entire space outside the sphere, squashed into a finite spherical volume. The conformal mapping of the inverse values in the unit interval is an elegant way to pack an infinite reflection into a finite space. But we still have a problem of lack of closure at the other end of the spectrum, where the number line extends out to infinity. This is a paradoxical problem that has plagued mathematics since day one. The solution is to provide the same kind of closure at this end of the number line as what we see within the unit interval. What we want is the same kind of conformal mapping over here in the number line as we have in the inverse part of the number line, where we can pack values all the way to infinity within a finite range, and then we'll have full closure in our mathematics. The way to achieve this is by way of a stereographic projection of the number line onto the number circle. Picture a unit circle centered around the origin, and for each value on the number line, for instance value 2 here, we find its projection to a point at the top of the circle, and we represent this value 2 as this point on the circle, and 3 is 3, and 4 is 4, and so forth. And using this scheme, by the time you get to the very top of the circle, you are actually at infinity. Now, if we take this conformal unit circle and unwrap it into a line that stretches from minus pi to pi, but represents numbers from minus infinity to infinity on a finite representation, this is the way to achieve closure in our number line. Here's a simulation of a space with this property. Here's point P, and point P can range from 1, which is its value here, all the way up to here's 2, 3, 4, and by the time it gets to here, P is at infinity, and its reciprocal has arrived at 0. So here we have a number line that occurs in a finite space, is trapped within a finite sphere, but otherwise works the same as our number line does. And the curious thing is that now the relationship between the point and its reciprocal is a simple mirror image in this conformal space from one conformal space to another. It makes a simple mirror symmetry that is very compelling. David Hestenes' conformal mapping, developed by way of his projective mapping, another elegant solution to dealing with the problem of infinity. The projection requires a supernumerary dimension, an extra dimension. So, for example, in three-dimensional space, it requires a fourth-dimensional vantage point, which is something that's difficult to imagine. Therefore, the concept is usually depicted for two-dimensional Euclidean space. Consider this a section of the infinite Euclidean plane, and we want to create a finite representation of it. We do so by erecting a vector in the third dimension and viewing the Euclidean plane from the vantage point of that vector. So this transforms, for example, every point along the x-axis over here into rays that project towards that point. And then we insert a projection plane for those rays to project onto, creating a perspective projection of the Euclidean plane, which can see all the way to infinity. Now, it's hard to imagine this process happening in 4 dimensions, but we can see the 3-dimensional result of a 4th-dimensional projection, for example, with this model of a room that is built with the perspective built in. In other words, these walls are not rectangular but trapezoids, and that the model really does shrink into the distance. And that means that if you extend these two converging lines to the point where they meet, that point represents infinity. It is possible to make this kind of projection in a 3D model as if you were viewing it from a 4th dimension. There's a dimensional reduction that occurs when Clifford algebra is used in projection. For example, this point in Euclidean space is represented by this projection vector, but where that projection vector projects onto the projection plane, it reduces back down to a point. This is analogous to a laser beam mounted on gimbals that is pointed towards a projection screen. The laser beam is a vector, but where it projects onto the screen, it reduces to a point. And by rotating the laser on its gimbals, we can move the point to any location on the projection screen. In order to present 2 points, A and B, simultaneously, we can present first the one and then the other and repeat in alternation in order to have both A plus B present on the screen. If we allow the two beams to morph between those 2 points with a multiplicative wedge product type morphing, then the projection beam becomes a bivector plane area, and where it projects onto the screen, it defines a line segment, just like a vector line segment. And so this now provides a means for projecting a line anywhere on the screen at any length and any orientation. The wedge product between 3 points projected on the screen defines the triangular area spanned by the 3 points. And due to the anti-commutative nature of the wedge product, the order of operations is significant. So A, wedge B, wedge C begins with A, wedge B, the line, and then this line is then modulated by wedge C, whereas in the other sequence, A, wedge C, wedge B begins with the line A, wedge C, and then that line is wedged back to B. The same principle should also operate in 3 dimensions with a 4-dimensional projection mechanism projecting into a 3-dimensional perspective model. 2 points A and B can be projected simultaneously by alternating between them. And if you allow for a multiplicative morphing between the 2 points, then it generates a line in 3-dimensional space between those 2 points. The wedge product between 3 points in 3-dimensional space is the triangular surface between them, and the wedge product between 4 points in 3-dimensional space generates, if they're all in the same plane, generates a rectangle. If a 5th point is added to the 4, then this defines, by a wedge product, defines a rectangular solid. And if that point is out at, scare quotes, infinity, then we have a representation that represents a square cross-section beam going off to infinity. The principle of projection is so primal to Clifford algebra that it is trivially easy to define a pinhole camera in Clifford algebra. We can define an image plane by the wedge product between these 4 points, A1, A2, A3, A4. Then we can define a focal point at one side of the image plane. Then for any point P in the volume of the image, we can define the vector from F to P as F wedge P, and we can compute where the vector projects onto the plane by a simple dot product between F wedge P and the image plane A1 wedge A2 wedge A3 wedge A4. Now, it's a fundamental property of optical systems that whatever transformation you can do in one direction, it can also do the inverse transformation by reversing the all of the ray paths. So the pinhole camera can be also reversed by projecting from a focal point through the image plane out into the 3-dimensional model. In fact, this is what perceptual function does. It takes a 2-dimensional retinal image and projects it into a 3-dimensional space of our visual experience. Now, there's a problem with this kind of projection, and that is that it can only really look in one direction at a time. You can't take 2 of these projections and put them together back to back and seamlessly merge them. The solution would be to project onto a surrounding sphere instead of a plane, so you could project in all directions. But don't put the viewpoint at the center of the sphere. In the first place, you could only ever use the lower hemisphere for projections on the Euclidean plane. Instead, the viewpoint is located at the top pole of the sphere, and the reason for that is that it confers some extraordinary invariances to the projection, which is a conformal projection. This is the first stage of the conformal projection in geometric algebra as proposed by David Hestenes. Here's a 3D depiction from Wikipedia of the stereographic projection of the 2-dimensional Euclidean plane. The Euclidean point A projects to conformal point alpha, which is the projection of A. Here's a stereographic projection of a square grid centered on the origin. The center of the grid, point 0, 0, projects to the nadir of the sphere. Points farther from the origin project higher on the sphere, and the outer perimeter of the grid projects around the top of the sphere. Here's the inverse of a chessboard with respect to a circle around its center. Here is a larger zoomed up version of the center, and you can see that around the outside of the circle there are 4 squares, white, black, white, black. They correspond to these surrounding squares, but then the rest of the squares going inward towards the center correspond to further and further out around the chessboard, and finally the outer perimeter of the chessboard is seen over here at the innermost rank of distorted squares. What this is an inversion of proximal and distal, nearness and farness. Nearer things are projected to the outer periphery, and farther things are projected in towards the center. Now, one of the extraordinary properties of the stereographic projection is that it projects circles in Euclidean space to circles in the conformal space. Here's a conformal projection of a circle projecting to a circle, and here is a straight line in the Euclidean plane, and that projects also to a circle in the conformal space, with the peculiar property that lines that go all the way out to infinity meet at the top of the sphere representing the infinite point. Circles and straight lines are the same shape in this space. The examples of conformal projection presented above involve a projection from a 2-dimensional Euclidean space for simplicity of exposition, but the conformal projection active in perception is a 3-dimensional phenomenon making use of a projection through a 4th spatial dimension. It is difficult to visualize operations in a 4th dimension. However, there is a peculiar feature of the conformal mapping that simplifies the visualization considerably. In 2-dimensional space, every direction in the xy plane extends outward from the origin to its own unique infinity. In projection, all of those infinities map to the same polar point at the pole of the sphere. This works only because every one of those directions in the xy plane is orthogonal to the z dimension that defines the north pole of the stereographic sphere. To expand into 3-dimensional conformal projection, a 4th dimension is required that is simultaneously orthogonal to xy and z. This 4th dimension is easier to visualize because of the fact that although every distinct direction in x, y, and z has its own unique infinity in that direction, all of those infinities map to the same single central point in the conformal projection, and that point is a finite unit distance away. So the entire squashed 4-dimension is contained within a 3-dimensional shell. It is a closed dimension that mimics infinity in a finite package. So we can visualize 3-dimensional conformal mapping as a finite spherical space where infinity maps to a singular point at its center. What we have here is the same bizarre mapping that we encountered in the inversive function. Here's a cylinder in 3-dimensional Euclidean space and its conformal reflection in the conformal sphere as the cylinder grows from finite to infinite length, and as it reaches the length of infinity, its ends in the conformal reflection meet at the infinite pole. And here's a square base with 4 pillars reflected in the conformal sphere. When I first encountered Hestena's conformal mapping, I was struck by the similarity to another conformally warped world that I had been studying, the perspective warp observed in visual experience. You can see this conformal warp when standing in a long straight road. The sides of the road converge to a point by perspective on the horizon ahead, and if you turn around, they converge to a point in the opposite direction too. And yet at the same time, the road appears straight and parallel and undistorted throughout its length. Objects in the distance appear smaller by perspective, and yet at the same time they appear undiminished in size. In case you've never noticed this warp of perceptual experience and may even question its reality, I conducted the hallway experiment in a hallway at the Scapin's Eye Research Institute. Subjects placed in the hallway were given 3 cardboard models, and they were asked to choose which model best matched their experience of the hallway. Not the geometry of the hallway as they knew it to be, but the shape of their experience of the hallway. Did it appear as a rectangular prism with right-angled corners and parallel sides, as in Model A? Or did it appear as a flat two-dimensional projection as depicted in Model C? Or did it appear somewhere in between, like a bas-relief perspective scene with lines converging towards a vanishing point, as shown in Model B? Subjects' responses were divided between Models A and B. Then the subjects were presented with a 4th Model D that was identical to Model B, except that it was etched with a perspective distorted grid, and the subjects were told that the grid represented the scale of the model. In other words, this was a scale model like any scale model, except that the scale varied with depth, such that the grid panels in the distance appear smaller by perspective, but they were the same objective size as the apparently larger panels in the foreground. When offered this alternative, all of the subjects chose Model D. This demonstrates a profound duality in spatial perception, whereby objects in the distance appear smaller by perspective, yet at the same time they are judged not to be smaller in objective size. Here's a 3-dimensional diorama that I built to demonstrate the principle. If viewed from exactly the right vantage point, it can appear indistinguishable. See, the curvature of that fence disappears and becomes identical to the projection you would see in a photograph. The retina is a spherical surface, and thus its fundamental coordinates are visual angles, and thus visual angle is the only component of external reality that is preserved through the retinal projection. It is this most certain and unambiguous information of the retinal image that is used to connect to the inversive conformal world and its conformal reflection across the unit sphere in the surrounding bubble world perspective that seeks to model the external world guided by the regularities detected in its inversive reflection. There's a compelling similarity between the conformally warped world of perceptual experience and the conformally warped inverse world of the stereographic projection. In some ways, these two warped worlds bear an eerie similarity, and yet in other ways they seem like polar opposites. The bubble world perspective is big in the middle and shrinks to nothing in the periphery, whereas the inversive world of the stereographic projection is big at the periphery and shrinks to nothing at the center, besides being also turned inside out. It finally dawned on me how these two worlds were related. One is the radial reflection of the other, conformally reflected across the surface of the unitary sphere. The large house in the foreground in the outer bubble world perspective corresponds to the larger house in its inversive reflection near the surface within the unitary sphere, while the smaller houses into the distance in the bubble world perspective correspond to the smaller houses toward the center of the inversive sphere. And in case you were wondering what happened to the percipient of this experience, there he is, nestled in between the two worlds, the bounding surface between the internal self and the external world. In my experience, I do see the surrounding world warped in a bubble world perspective, but I see no trace in my experience of that weird inside-out conformally reflected world, although I do perceive some of the regularities that are detectable only in that inversive world. I do perceive a circularity in an endless row of identical houses, and how progressing towards infinity is much like running on the spot in a hamster wheel. And here we see the conformal reflection of a 3-dimensional world in a 3-dimensional sphere that represents the entire world around it, with the only part missing being whatever is contained inside this sphere. The concentric inside-out mirroring between a central inversive conformal sphere of negative curvature and a surrounding conformal sphere with positive curvature offers an extraordinarily powerful system for representing geometrical form based on a very few foundational primitives. The outer bubble world conformal mapping offers a finite bounded space capable of representing an infinite unbounded space that can now represent space all the way out to infinity in all directions. The inner inversive conformal sphere at the center can be viewed as a kind of projection mechanism capable of projecting geometrical images into the outer projective space based on the symmetries reflected in the inner inversive space. Vectors in the conformal sphere project to points in the perceptual sphere, the radial length of the vector being inversely proportional to the radial distance of the point it represents. A vector of zero length projects to infinity at the periphery of the perceptual space. Two vectors presented simultaneously or successively represent 2 points in perceptual space. The wedge product between 2 points defines the line that joins them in perceptual space. It also defines a circular arc in conformal space. The inner product null space of that wedge product represents the whole line of which the line segment is a part, which completes to a full circle in the inverse conformal sphere. This is not just a single line through the center. It can represent a range of geodesics which appear curved but represent straight lines in that curved space. The wedge product between 3 points defines the circle that joins them. Circles and straight lines are the same shape in this space. And if one of the 3 points moves off to infinity, the wedge product defines a circle of infinite radius. A circle of infinite radius is a straight line that passes through the non-infinite points. The wedge product between 4 points defines the spherical shell that passes through those points. And if one of those points moves off to infinity, the wedge product defines a spherical shell of infinite radius, which is a plane that passes through the 3 non-infinite points. Spherical shells and flat planes are the same shape in this space. Here are some animations using the GA viewer demonstrating the principles of conformal geometry, showing only the objects in external Euclidean space, although the symmetries observed in this space reflect the symmetries in the inverse conformal world. Here are 4 points, A, B, C, D, disposed around an arbitrary origin, O. In conformal geometry, points are dual spheres of 0 radius. The dot product between 2 points is a scalar that is proportional to the square of the distance between them. The dot product, therefore, is a distance measure in conformal geometry. The dual of a point is a sphere, and the dual of a sphere is a point. Points and spheres are the same shape in this space. The wedge product between 2 points defines the point pair, or line segment that joins them. Actually, a point pair is a one-dimensional sphere, i.e. 2 points that are equidistant from some center. The dual of a point pair is a circle whose radius is proportional to the separation between the 2 points. The dual of a circle is a point pair. The wedge product between 2 points and infinity is the straight line containing the 2 points. Infinity is a single point that can be found in all directions. The dual of a line is its normal plane. The dual of a plane is its normal line. The wedge product between 3 points defines the circle that joins them. This only really makes sense in the inverse conformal world where circles and straight lines are the same shape. It is a symmetry that shines back out to the Euclidean world. See how the circle morphs as its defining points move. As the third point passes between the other two, the circle momentarily becomes a circle of infinite radius, i.e. a straight line. The wedge product between 3 points and infinity defines the infinite plane that passes through the 3 points. The wedge product between 4 points defines the sphere that passes through those points. See how the sphere morphs as its defining points move. As the 4th point passes through the plane defined by the other 3, the wedge product momentarily becomes an infinite plane before turning completely inside out through infinity. There are a number of curious properties of the conformal model that are a result of its circular closure. Rotation is double reflection. Translation is rotation about infinity. We learned in Clifford algebra that rotations can be expressed as double reflections. In the conformal model, translation is a rotation about infinity. Indeed, all Euclidean transformations can be expressed as reflections in the conformal model. Scaling requires a reflection through a curved mirror, which is exactly a conformal reflection. The fact that the elements of Euclidean geometry, points, lines, planes, and spheres, are all essentially the same shape in conformal space, and the fact that so many Euclidean transformations can be expressed in terms of reflections, is highly suggestive of a computational mechanism in the brain based fundamentally on reflections and projections between spherical elements in a conformal model. We can now see the full implications of the principle of closure manifest at so many different levels in geometric algebra. Closure is not a property that makes for an accurate rendition of external reality. Closure introduces a circular warp in the representation of Euclidean space, bending straight lines into curved geodesics and flat planes into spherical surfaces. It presents a multiplication that goes round and round instead of in and out from the origin. The purpose of closure in mathematics is the same as for the odometer or the digital register. It provides a computational mechanism that will never run off the edge of the page or roll off the end of the register. The register simply rolls back around through zero, wrapping infinity up in a finite circular reel. There never were straight lines in the brain. The number line never extended to infinity. Like the geometry of perceptual space, the number line only approximates the linearity of the true theoretical number line, and it does so adequately only in regions relatively near to the origin. It fails catastrophically at the point where it meets infinity because infinity falls infinitely short of true infinity at the end of the number line. Closure is what allows the mind to encompass the infinite without having to be itself infinite in extent. Closure is a practical solution to the problem of modeling an essentially infinite world in a finite bounded representation. Like the dome of the night sky, closure in mathematics is evidence of the limits and limitations of our own mind. The history of algebra has been the history of an incremental discovery of an apparently pre-existing structure. At first, the operations of mathematics were seen as convenient tricks or techniques useful for computing quantitative results. Math seemed at first to be a human invention, as individual mathematicians were credited with inventing different tricks or techniques that simplified calculations. But as more of mathematics has been revealed, the more it has become clear that mathematics is a pre-existing structure with an inherent logic of its own. And new additions to math are not arbitrary inventions, they are incremental discoveries of the hidden logic underlying mathematics. Negative numbers and the square root of -1, it seems, were there all along waiting to be discovered, implicit in the structure of the number line and the algebraic operations on it. But if mathematics is a pre-existing structure, what is that structure and where is it located? The time has come to finally reject the romantic notion of mathematics as an objective, external entity with independent existence in an orthogonal dimension inaccessible to scientific scrutiny. The time has come to recognize mathematics for what it is, an artifact of the way our brain makes sense of spatial reality. Mathematics has physical existence and embodiment in the human brain. But where in the fleshy, blobby gray matter of the brain would you begin to look for geometric structures like the number line and the crystalline perfection of points and lines and planes? The brain just seems like the wrong kind of organ to express that kind of crystalline perfection. Mathematics is not the only artifact of the computational principles of the human mind. Many have observed the intimate relationship between mathematics and music, with its geometric harmonies and periodic rhythms, its cyclic patterns of melody reminiscent of the rotation of a Clifford algebra spinner. The periodic ticks of a metronome mark out periodic intervals of time as regular as the number line. Could it be that music is yet another manifestation of the mechanism of mind? That would at least resolve the long-standing mystery of the origins and evolutionary purpose of music. And if music reveals the mechanism of mind, it also reveals mind to be composed fundamentally of oscillations. It is no accident that Clifford algebra provides such an elegant model of cyclic oscillations, such as the spin of elemental particles. That is because Clifford algebra is patterned on the oscillations in the human brain. Yet another manifestation of the principles of perception is seen in ornamental art as seen in churches, cathedrals, mosques, and palaces all over the world. Ornament is visual music with its many symmetries and periodicities and crystalline perfection. If visual ornament is indeed an artifact of the computational principle of the mind, then visual ornament reveals a mechanism based on symmetries and periodicities, which are also properties of standing waves, as seen in Chladni figures obtained by bowing a steel plate with a violin bow. Harmonic resonance is a self-organizing principle of physical matter expressed in terms of symmetries and periodicities. The complexity of the pattern that emerge far exceeds the complexity of the mechanism that produces them, which is just a homogeneous steel plate. Here are a sample of possible Chladni figures on a square plate and a circular plate. The circular patterns can emerge at any orientation. Chladni figures demonstrate the basic computational principle of the brain, a principle that requires no complex mechanism besides spontaneous emergence of standing waves, a principle that is consistent with the crystalline perfection of the number line and the concepts of points and lines and planes. And if that is not yet evidence enough for harmonic resonance in the brain, Heinrich Klüver administered LSD to volunteers who then lay in a dark room and reported their visual hallucinations. The subjects reported patterns described as grating, lattice, fretwork, filigree, honeycomb, chessboard, cobweb, funnel, tunnel, cone, and spiral that spontaneously appeared. The patterns were exceedingly rich and complex, but each pattern appeared only for a fleeting moment before morphing endlessly into other patterns. Geometric patterns are the primitives of visual perception. The significance of all this symmetry to the principles of perception is revealed by psychedelic art. For example, this spectacular piece called Inner Sanctum by Luke Brown, inspired by the salvia experience. If the human mind spontaneously hallucinates images so rich with symmetries and periodicities, that also suggests a harmonic resonance mechanism capable of generating hundreds of such hallucinated scenes per second. Indeed, the fact that we can instantly recognize the symmetry of a kaleidoscopic pattern is itself evidence for a symmetry-based recognition system, one that must operate in parallel to solve this intractable visual problem so rapidly. The hyperbolic geometry of the conformal mapping is in evidence in Escher's woodcut circle limit 4. If we accept the overwhelming evidence that mathematics, music, and ornamental art are all artifacts of the computational mechanism of the brain, then we can begin to study the brain based on the properties of those artifacts. Clifford algebra in particular suggests the operational principles of the elements of perception, or how the brain constructs geometric objects out of the basic primitives of scalars, vectors, and multivectors of higher dimensions. Clifford algebra reveals that the computational operations of the brain are explicitly spatial in nature, and that spatial nature is essential to their computational function. The concept of duality is highly suggestive of the relationship between a standing wave oscillation, as on a Chladni plate, and the nodes of that wave, which are the regions where there is no oscillation. The pattern of nodes determines the shape of the vibration just as well as the vibrations themselves. For example, the duality between a sphere and its central point is suggestive of a spherical standing wave oscillating between the spherical surface and its central point of symmetry. The conformal mapping of geometric algebra offers a clear hint as to how a finite but explicitly spatial model can encode an essentially infinite space in a manner that seems invisible to the percipient. We have the illusion of being in a practically infinite space when outdoors, although our experience is bounded by the dome of the sky. Anything farther than that horizon is usually insignificant to our experience. The fact that a conformal projection is itself a form of reflection, and that reflection is a most fundamental operation in geometric algebra, suggests that the computational mechanism of the brain is built up out of simple basic elements, as are Clifford algebra and geometric algebra. The principles of phase conjugation and nonlinear optics demonstrate how a wave-based system can perform computations. Whereas linear waves pass through each other transparently as if the other waves were not there, nonlinear waves warp the medium sufficient to deflect other waves, and this provides an essential control mechanism where one wave can modulate another in a manner that is suggestive of a bivector formed by the wedge product between two waves, and that bivector in turn can act to deflect a third wave by Clifford multiplication. I have proposed a model of perception based on the principles of phase conjugation. The many phase reversals of Clifford multiplication and the fact that angles are represented by their projections onto the basis coordinates is suggestive of a phasic cyclic system like the Clifford vectors analog electronics analogy. I propose that the next step in investigating the computational principles of the brain would be to devise a phasic cyclic analog oscillatory model of Clifford multiplication as an image projection mechanism capable of generating synthetic images. The discovery of Clifford algebra and its subsequent elaboration into geometric algebra marks a profound turning point in the history of mathematics, where we can finally realize what it is that we have been studying all along. When Hamilton invented his quaternions and Descartes plotted numbers graphically, when Gibbs invented vectors and their dot and cross products, when Hermann Grassmann invented the wedge product, unbeknownst even to themselves, these mathematical pioneers were unwittingly studying the principles of operation of the human mind implemented in the brain. Now that we know what it is that we are studying in mathematics, we can begin to reverse engineer the operational principles of our own brain under the guidance of Clifford and geometric algebra.